Let's start with a problem that was similar to one you turned in today, but is worth doing again because it's kind of tricky. We're going to integrate e to the 2x times cosine of 3x. It's going to be convenient to give this integral a symbol. Call it I for integral, okay? Not the number I for integral. We're going to use integration by parts, which, of course, as we've been doing, means we need to decide what u should be and what v prime should be. And it's not clear what is the best choice here. Remember, the first most important bit of advice is v prime should be one of the factors that's easy to integrate. And u should be something that hopefully, at least, it's nice when u prime is simpler. However, either choice, whether you let u be e to the 2x and v prime be cosine of 3x, or u be cosine of 3x and v prime be e to the 2x, the level of difficulty is about the same, and you can integrate in either case. Let's just choose the same as the order that we see here. Let's let that be u, e to the 2x, and v prime be the other factor, cosine of 3x. And let's just see what happens when we do this. Find u prime, find v, be careful. In finding v by integrating v prime, I'm going to do a substitution in my head. I'm really imagining letting w be 3x, dw would be 3dx. And if you do that, and if you're careful, you'll get 1/3 sine 3x as what v is. Then use the integration by parts formula. As usual, u times v minus the integral of v times u prime. Everything does depend on x. The product of u and v, look where I'm pointing, is going to be 1/3 e to the 2x times sine of 3x. 1/3 e to the 2x times sine of 3x. And minus the integral of the product of v and u prime, look where I'm pointing again, minus the integral of the product of these two things. That's going to give me a factor of 2/3 that can be factored out in front of the integral. So I'll get a minus 2/3 times the integral of e to the 2x sine of 3x. Now, what you typically hope for with integration by parts when you do it is that you get a new integral that's easier to do. But that didn't happen here. We got a new integral that's about the same level of difficulty as the original integral. But it does involve a sine instead of a cosine. So maybe if we do it again, we'll get yet another integral that involves a cosine, and maybe, just maybe, we can solve for it. Yeah, there was an example like this in the book. You did one like this on your homework if you follow that example. Do it again, but be consistent. If I've let u be the exponential function and v prime be the trig function in the previous integration by parts, do the same thing again. For this integral right here, let u be e to the 2x, v prime be sine of 3x. Once again, find u prime and v. A little extra tricky here. Integrating sine gives you negative cosine, and we also will have a 1/3. So we'll get a negative 1/3 cos 3x. Lots of places where mistakes can happen. You have to be very careful. Minus signs, I think, especially, as well as some fraction. Continue. Don't forget the first part. If you forget that, you'll get the wrong answer. 1/3 e to the 2x sine of 3x minus 2/3 times this integral, but that integral I need to do by parts. I better use parentheses because it's something minus something else. I'm going to subtract 2/3 times that entire thing. I better use parentheses if I want to be extra careful. Product of these two, u and v, is negative 1/3 e to the 2x cosine of 3x minus the integral of the product of these two things. you see you're going to have two minus signs. That's going to make a plus sign. We're also going to have a 2/3 that can once again be factored out. Two minuses again make a plus. This is going to become a plus. 2/3 integral e to the 2x cosine of 3x. Guess what? This thing right here, that's the original integral I. You can look and see. Yep, same as the original integral. Integral of e to the 2x cosine of 3x. We've got that here. Now just do some algebra. Right, rewrite the first part, distribute the 2/3 through the parentheses. Negative 2/3 times negative 1/3 is positive 2/9 e to the 2x cos 3x. And then we have a minus 2/3 times positive 2/3. That's minus 4/9 times I. I is what we want to solve for. I is the integral. I got an equation, an algebraic equation for I. Just algebraically solve for it. Where does the plus c come from? I mean, you could add it on here, though we are going to ultimately do a little bit of multiplication to solve for I. You could call it something different like C1. That's actually what I did in the first class, but I'm just going to put it on at the very end. Add 4/9 to both sides so that it cancels on this side. But if I do it to the right side, I also have to add 4/9 side to the left side, the original integral. I get I plus 4/9 I. I is the same as 1 times I, and 1 is 9/9. So getting that common denominator of 9, 9/9 plus 4/9 is 13/9. 13/9 I equals 1/3 e to the 2x sine 3x plus 2/9 e to the 2x cos 3x. Now multiply both sides by 9/13. And don't forget to add on the plus c at the end. We get cancellation here. I, the integral we want to know, is going to be 1/3 times 9/13. The 3 will cancel with the 9, leaving an extra factor of 3 on the top here. 3/13 e to the 2x sine 3x. And then 2/9 times 9/13. The 9s will cancel. And you're left with 2/13 e to the 2x cos 3x. Yeah, now tack on a plus c at the end. There we have it. Does it work? We could certainly check by differentiation, though that would be a pain. You'd have to use the product rule in both spots and the chain rule a number of times, 4 times, and then you'd have to simplify with fractions and stuff. Sounds like we better just use technology here. You got to be cautious when doing integrals involving trig functions, however, because there's various kinds of ways to write the answer because of all the trigonometric identities that are out there. There's hundreds of them, thousands of them even. It's possible Mathematica may not return the answer that looks like this. And if we want it to look more like what we got, I better do / expand. It does look the same, though Mathematica would fail the gateway, right? They don't program Mathematica to put the plus c in there. They know you should, but they just don't want to bother. But for the gateway exam, you need to put the plus c in there to get the problem right. You miss the plus c, you'd get 0 on the gateway. Okay, so make sure it's there. Looks good. Could also be checked by differentiation. Capital D will differentiate. I can copy and paste the function in there, put a comma x, because that's the variable name. And yes, it simplifies to our original integrand, e to the 2x times cosine of 3x. Okay. Let's do another example where we once again use integration by parts. Possibly twice, but in this example, I'm going to show you that you actually can avoid using it twice in two different ways. The integral is going to be to integrate cos squared, and it's common in these situations to integrate, to call the variable theta. You're going to have a problem like this to Friday. You'll be integrating sine squared theta. I mentioned that products of powers of cosines and sines does come up on the gateway. I believe this one doesn't. However, I want you to know it anyway for the next exam and for homework. It's a pretty important integral. I did think of some applications. They're mostly to multivariable calculus and the applications of multivariable calculus. In multivariable calculus, when you're doing double and triple integrals, yikes, no, they're fun. You can use different coordinate systems like polar coordinates and spherical coordinates, if you've ever heard of those. That makes the integrals actually simpler, though when you do so, they often you end up integrating things like this. So it is a useful thing to know how to integrate this. And you might be somebody who says, well, I can always just have the computer do it for me, or ChatGPT do it for me, or maybe even just Google it, and I'll probably get the right answer. So why do I ever need to do this? One practical reason I can give you is that when you're in your more advanced classes, the professor's doing some calculation, they may do it the classical way by hand. And so it's like, if you don't know what's going on, you won't know what they're doing. You might be like, not really paying attention. And then you look at the board and what in the world they do there? You want to understand things, okay? So that's one reason, a good reason. Maybe you also want to say doing things by hand is still good because it makes it feel more real. And when you check it by differentiation, it reminds you all what it all means. Okay? And it's good to somewhat be familiar with what kinds of integrals can be done and what kind of integrals can't be done so easily. And that just takes experience and practice. Anyway, coming back and doing this by parts, what should u and v prime be? Evidently, I guess they both have to be cos theta. That's the only choice you could probably make that would make any sense. What happens if I do that? U prime will be negative sine theta, and v will be sine theta. U times v will be cos theta times sine theta. Now, I almost always put parentheses around my inputs for cosine and sine. I'm not bothering here because it would just be too many parentheses. That's u times v. U, v, minus the integral of v times u prime. Multiply these things. The product of those is negative sine squared. The two negatives will cancel. So we add the integral of sine squared. This ultimately is, whole thing is minus the integral of v times u prime. But the two minuses cancel and gave a plus. Yeah, it doesn't seem like we got very far, right? Cos squared theta got transformed to sine squared theta. So do we do parts again, just like the last example? No, you can avoid it. Replace this with 1 minus cos squared theta. Right, that's an identity. Those are equal. You will still algebraically solve for the integral you want to know, so I could still call it I, the integral I want to know, but I won't bother. Don't forget the first part, cos theta, sine theta. Looks like I'm going to add the integral of 1 and subtract the integral of cos squared theta, which is what I want to know. This integral is nice and simple. That's just theta. Now add the integral you want to know to both sides to cancel it on the right. And get 2 times it on the left. I add it to one side, I got to do it the same to the other side. So I get 2 times the integral I want to know equals cos theta sine theta plus theta plus c, but I'll just put the c on at the end. So the integral I want to know, integral of cos squared theta, is 1/2 of this plus c. I'm going to write the theta part first. 1/2 theta plus 1/2 cos theta sine theta plus c. But that's not the only way to do the integral. I'm going to show you another way that uses a trigonometric identity right from the start. And I highly recommend doing it this way in the future, including if you take multivariable calculus. Well, what do? Do I replace this with 1 minus sine squared theta? That wouldn't seem very useful, except to get the theta out. And then replace the sine squared theta with 1 minus cos squared theta, and then solve for the cos integral of cos squared theta. Doing that actually doesn't work, because what you end up with is an equation like 0 equals 0 or something like that, or a constant equals a constant. It turns out to be better to use another trigonometric identity that most people don't take the time to remember, but I'm suggesting that from now on you try to remember this. Well, do I need to know it for the gateway? Again, I'm not going to give you this kind of problem on the gateway, though I could. It just hasn't been traditional for Bethel as a department to give this particular one on the gateway. We do give on every gateway version products of powers of cosine and sine where one of the powers is odd. We already did an example like that. That shows up on every example gateway. But this one doesn't. However, it's a very useful integral. And here's what you want to use. Cos squared theta is 1/2 plus 1/2 cos 2 theta. I'm using parentheses there around the 2 theta, but I probably won't hereafter. These two things are equal for all theta. Equal for all theta. The equality of those two things is a trigonometric identity. Probably you don't remember it, but I'm saying it's worthwhile to try to remember this in the future. On your homework, you'll use a similar identity that sine squared theta is always equal to 1/2 minus 1/2, not sine 2 theta, but cos 2 theta. How can that be? Well, I'm not proving these, so you're just trusting me. That's a 2 there. You're just trusting me, but do notice that if I add these two equations, on the left side, I get cos squared theta plus sine squared theta, which is 1 for all theta. And on the right side, if I add these two things, I get 1/2 plus 1/2 is 1, and those two parts cancel. I get 1. It does work to add them to see that you get something that's true. That's not a proof that these are equal, but it maybe helps you believe it a little bit more. Why is this helpful? Is because this is now easier to integrate. Integrate 1/2, get 1/2 theta. Oh, yep, that's matching. Integrate this piece, and you get something that looks like it doesn't match. I'm doing the integral in my head. I get that. Don't forget the plus c at the end. So which is it? Which one's right? They're both right. Certainly 1/2 theta is the same in both. These two things are actually equal as well. That's yet another trig identity based on a simpler version, a so-called double angle formula that says sine of 2 theta is always equal to 2 sine theta cos theta. So if you make that replacement here, The 1/4 and the 2 cancel to give you 1/2. 1/2 cos theta sine theta, just like I have up here. They are the exact same function. There's another trig identity. That one's worth remembering too. On exam 1, you can use a note card, but it's worthwhile to try to remember these. These are some of the more common ones used for integration. Then class, we're going to do an example with a table. We're going to integrate cos 3 theta times sine 4 theta, a cosine and a sine with 2 different frequencies, you might say, 2 different periods for the graphs. Cos 3 theta has a period of 2 pi over 3. Sine 4 theta has a period of 2 pi over 4, which is pi over 2. You could do this with trigonometric identities right from the start. For example, you could use these trigonometric identities, product of sum identities that I found on Wikipedia for products of cosines and sines. You could do that, but instead we're going to use a table of integrals in the back of the book, at least in my print version. If it's not in your print version, you can look it up. Looks like property 12 is the one we want, because we have a product of sine and cosine with different frequencies there. Identify what the A is and what the B is, and then use it. These integrals are very useful in Fourier analysis when you're computing Fourier series, doing these kinds of integrals. So if I compare these integrals here, it looks like the B is 3 and the A is 4. Using the formula on the right side, right up here, I get 1 over b squared minus a squared is 1 over 3 squared minus 4 squared times, the book uses square brackets, but I can use parentheses, b sine ax sine bx, b is 3 sine a is 4. I'm going to go back to theta like I'm doing here instead of x. Sine 4 theta, sine 3 theta, and then plus a, which is 4, cos 4 theta, cos 3 theta. And then don't forget your plus c at the end. Now simplify a little bit. This is the same as 9 minus 16 is negative 7. This is a negative 1/7. So distributing that through, we're going to get negative 3/7 sine 4 theta, sine 3 theta, and then a minus 4/7 cos 4 theta, cos 3 theta, plus c. That's what the table gives you. If you try checking this with Mathematica, turns out you get something that looks different. The original integral is cos 3 theta, cos 3 theta, I can make a theta by doing escape, th escape, times sine 4 theta, d theta. It's going to look different, but I actually did graph these after the first class, this function here and in Mathematica, and I saw they were the same. In fact, I've got another notebook where I'll show you the graphs. There they are. Well, it's the same graph. If you're unsure, you could add like 0.1 to one of them. And yeah, they are the same function. I'm going to send a message about that because I didn't know that they'd turn out right at the end of the first class. So you'll see a message from me saying, hey, it was right. But now you know it is right. Even though they look different, they are the same. Okay. Sometimes they differ by constant, though. That's possible. All right. Have a good day.